Okay, here we want to try something really cool. So we want to find the antiderivative of this sum, and the sum is given as the sum as k starts from 2 to infinity of x over k times k minus 1. Okay, great. And we're going to find the antiderivative over the x variable. So as you can see, this sum doesn't really have anything to do with x. So maybe you can put the x out front, that is outside the sum, but still inside the integral sign. And then if we do that, we're just going to have the sum as k starts from 2 to infinity of 1 over k times k minus 1. Okay, given that x can be pushed out of the sum, right, but still inside the integral because we have to integrate it over the x variable. Okay, great. So we now have this sum alone, and whenever we have an infinite sum this way, we usually look at what we call a partial sum by saying that this sum is going to be the same thing as, technically the same thing as the sum as k starts from 2 to n of 1 over k times k minus 1, right? And then we are looking at this when n tends to infinity. So we look at limits. So as you can see, this n has replaced the infinity. That means this limit as n tends to infinity will account for it. All right, great. So technically they are the same. All right, great. So given that, then what we just have to do right now is to look at this sum. Then we later find the limit. Then the way we take this is this. We would first of all want to resolve this to its partial fractions. So I'm going to have to equate this again. Let me put it down here. To the limit as n tends to infinity of the sum as k starts from 2 to n of. So we're going to resolve this to its partial fractions. And since we just have two factors right there, we're going to have two fractions. Alright, great. And then the first one will going to be k, and then the second one will be k minus 1. Maybe let's just put an addition sign here. Alright, great. So to figure out what this first numerator will be, we just have to find ask ourselves what will make this denominator to be 0, the denominator of this first fraction. Well, it's going to be 0 when k is 0. That's just by using the cover-up method. So we come over here, substitute 0 wherever we find k, covering this particular k up, the particular factor we are looking at right now. So we're going to cover this up. We're going to have 1 over 0 minus 1. That is just going to be negative 1. And that is the numerator of the first fraction. Okay, great. So to figure out what the numerator of the second fraction will be, we look at what value of k will give us 0 in this denominator. Well, if k is 1, this denominator will be 0. So we come over here, cover up that factor, k minus 1, then substitute 1 into the other, into k in the other, still in that expression. So we're going to have 1 over 1, which is just 1. Okay, great. So we've successfully resolved this to its partial fractions, and this will add up to that. All right, so since we're done with that, then the next thing is to find out the sum. So I'm going to equate this to the limit as n tends to infinity of. Now, when k is 2, we're going to have negative 1/2 plus, when k is 2, we're going to have 1 over 1. So you notice that, right? Okay, let me do this. And then when k is, so we have a sum, so we add this. When k is 3, we're going to have negative 1/3. And when k is 3, we're going to have plus, this is going to be 1/2. We continue. When k is 4, we're going to have negative 1/4 plus 1/3. All right, and if you can see that, that means we're going to add them up till we get to this term right here, which is just when k is n, right, from 2 to n. So we're going to have negative 1 over n plus 1 over n minus 1. So as you can see, these terms are cancelling, right? This negative 1/2 plus 1/2 will get to 0 because they're just equal and opposite in sign. Okay, great. Negative 1/3 plus 1/3 will cancel, and you can see this, meaning that some terms will continue. And in this order, you know that negative 4 will definitely cancel out with some positive 4 here, and including this one here. This term will cancel out with some term over there, leaving us with just positive 1 and negative 1 over n. So maybe I will clean this up, and then we're going to continue from this line. Okay, so you notice that here we're just going to have the limit as n tends to infinity of, we have positive 1 here, which I've written out there, and then all the way to negative 1 over n, which I've written out here. So I can get away with this. And now we just have to figure out what the limit will be. Well, clearly, as n tends to infinity, 1 will just remain 1, because the limit of the difference can be taken as the difference of the limit. And then as n tends to infinity of 1 over n, well, that tends to 0 from the right. Anyway, it's still 0. So we just have here to be 1. So this is the limit. And this limit is in fact equal to the sum, as k starts from 2 to infinity, of 1 over that. So since we've gotten that, let me just map it out this way. Then we're going to have this to become the integral of x times this sum. Well, the sum is just 1. And then we do that over the x variable. And this is quite easy because x times 1 is just x, and then the antiderivative of x is x squared over 2. And since we are taking an indefinite integral, we can add an arbitrary constant. And this right here is the antiderivative of the sum over the x variable. Alright, great. Okay, thanks for watching. Please subscribe to my channel.